Good afternoon everyone. Thank you for joining me for this video on continuation of vectors. Mr. Ish over here. I have presented several videos on vectors. The formalized approach I have presented, which required calculators pretty much all the way through with regards to the calculations. Today this video is sort of a break from that dependency on the calculator, in that I will present a specific example how it was done in the old way. Imagine if you were a pilot within around World War I or pre-World War II time frame. Back then calculator was not invented, so how would they have determined vectors, especially in terms of flying? And I'm pretty sure, based on my research, that the planes back then could not travel very fast in terms of their miles per hour. We have a hypothetical situation where here we're going to calculate the resulting vector, and we're going to calculate the resulting direction by means of the traditional approaches. We have a plane over here, a pre-World War II or a post-World War I plane, which can fly at a top speed of 180 miles per hour. 180 miles per hour seems like a reasonable speed, and you're flying in a plane against, in some direction of a wind which has its own speed of 60 miles per hour. So let's give a certain direction over here to both of these items. The plane is flying at a direction, let's say north, bearing 15 degrees east. North 15 degrees east, and the wind is opposing you, let's just say in a southwardly direction, 45 degrees west. Very roughly, let's do a quick graph of this just to see where we are, and we're going to formalize it all by means of the old way techniques. If you're going north 15 degrees east, here's your north line, here's my south line, and this is how they did it back in the day when there was no calculator. Let's make this neat. 15 over here, 15 degrees east of north. 15 degrees east of north is in this direction. You're going in an eastwardly direction. You're going to do 90 minus 15 and you'll get 75 degrees. So we know our plane is going 75 degrees with regards to this reference horizontal. Now let's talk about the wind. It's blowing south 45 degrees west. Here's my south, but it's blowing in a westerly direction from the south, but at a 45 degrees angle. 270, which represents this over here, 270 degrees minus 45, what that would be. It would be 225 degrees. 225. So the wind is going 225 degrees in this direction. Now all we have to do is basically determine what the resultant would be of this plane against these conditions. And we cannot be using a calculator over here. We have to use the basic approach of a ruler and a protractor. So let's rewrite what we have over here. We have 180 miles per hour north, 15 degrees east, which is really 75 degrees. And the wind over here is 225 degrees. In a 225 degrees, let's erase this and make some space. How would we proceed with regards to this question? Because this is exactly what they had to deal with back in the day. No calculator. The first thing you want to do is have a measuring device. 180 miles per hour, it represents your magnitude. This 60 and 180 represents magnitude, and vectors have two components. There's a magnitude and there's a direction. I have the magnitude laid and I have the direction laid. Now all we have to do is convert this magnitude in some sort of into some other item which you can easily measure, or you can easily draw. If we were to convert the speed into length, and imagine that length represent the distance, or the length represented the speed, we can easily convert 180 miles per hour by just the process of analogy to 18 inches or 18 centimeters. If you're using a ruler, assume 180, because you could just cross out these zeros and make it 18 and 6. You could, in essence, depict your vector as having a magnitude by converting the speed into length. And there'd be nothing wrong with that. The 60 would become 6 inches or 6 centimeters, and 180 miles per hour would become 18 inches or 18 centimeters. So we have already solved a big part of this problem by converting this into a usable quantity. The 75 and 225 degrees are easily dealt with by means of a protractor. That's not a problem at all. All we got to do is now plot this out and determine our resultant. And the process by which we're going to do that is a parallelogram method. Now I've created some space over here by rewriting what we have as in terms of the facts of the plane and the wind. Remember, we're talking about doing the vectors the old way, and we're going to be using this example to demonstrate how it was done. Just consider this as a fun exercise. We converted the speed of both into 18 inches and 6 centimeters, and there's nothing wrong with you even converting this into centimeters, inches to centimeters, in case of if you don't have a large enough ruler which can accommodate 18 inches, you can always do it in terms of centimeters. Nothing wrong. You can convert it into whatever units you want, so long as you remain consistent. Now all we have to do for the parallelogram method, remember when it comes to these drawing methods, the diagrammatic methods of vector additions, because when we're determining the resultant of all of this, we're looking at vector addition. The whole analysis involves on accuracy, and you have to be accurate. So let's look at the plane. Let's draw a plane having a dimension, the speed dimension of 18 centimeters, but at 75 degrees. Here I have a protractor. I'm going to put it right here at the origin, and I'm going to mark it's 75 degrees. You know how to use a protractor. Remember, I'm showing you how things was done in the old way. Here's my 75 degree dot. Now all I have to do, and I'm going to use centimeters over here. I have a small ruler over here. I'm using purposely a small ruler so I don't start hiding too many things in terms of blocking your view with a large ruler. I'm going to draw from the origin. I have a 14 centimeter ruler over here, so I just have to go up to 18. I'll do 14 all the way, then I'll add 4 on the top. And remember, you got to be accurate over here. From the origin, let's go 14, let's add 4 more. We'll add 4 more. And then we'll get our 18 centimeters. Here's 18 centimeters or 180 miles per hour at a direction of 75 degrees. Now we have to do the wind. The wind is easy. It's 225 degrees. Always plot the angles first, the direction. I'm going to aim the protractor upside down with a 90 on this 270 degree line, and I'm going to mark 45 degrees. Now remember, this is how it was exactly done. We take calculators very freely over here, their use and to our advantage, but this is exactly how it was done. I'm going to mark a 45 degree mark over here because 270 minus 45 will give me 225. Now all I have to do is mark 6 centimeters. 6 centimeters, but again from the origin in the direction of 225 degrees. So I'm going to go 6 centimeters. And remember, when we're talking about vectors, you're talking about magnitude and direction, and everything has to be accurate, especially for the parallelogram and the triangle method. You can see now everything is accurate in with regards to those dimensions. The wind at 45 degrees west of this 270 degree line, or south 45 degrees west, and you have a plane 180 miles per hour but 15 degrees east of north. Now let's do the actual parallelogram method. Now for the parallelogram method, you have to be again accurate in terms of drawing a parallelogram. You basically have two sides of a parallelogram, and you know all parallelograms have a depiction which looks something like this: two pairs of parallel sides. Not only they're just two pairs of parallel sides, but they're two equal, the pairs are equal in terms of length. This right here will be equal to that, and that will be equal to that, and of course they're parallel. The pairs are parallel to one another. So here we have to be accurate again. Now the process by which we're going to do that is we're going to draw a parallel line to this long line, but again the long line must be 18 centimeters from this, but at an angle of 75 degrees. Look what we'll do over here. We'll draw a reference horizontal over here. A reference horizontal. From this point over here, we'll do a reference horizontal, because from this reference horizontal, I'm going to measure from this 75 degrees, and then from there I'm going to draw an 18 centimeter line. But let's do that measurement first of 75 degrees. And you know, you've seen in the old movies, they had protractors and they had angles and rulers in their hand as they were measuring their vectors, because they were measuring it because they needed to know where to go, how to go, and what were the environmental factors that were influencing their trip. So 75 degrees over here is marked. Now let's do 18 centimeters from this line in that direction. 18 centimeters. I have a 14 centimeter ruler. I'm going to do 14, and then I'm going to do a 4 on top of that. But we have to remain accurate over here. And you can see how easy the calculator is with regards to all of this vector analysis. I've gone my 14. Now let's add 4 more. My fingers might be erasing things on the side, but I'll try not to do that. Let's add 4 more, and here it is. All we have to do is connect this and we'll get the other pair of the parallel side, and it will be to accuracy. If you were to draw a reference horizontal over here, it would be 225 degrees with regards to that new origin. But look over here, we've gotten our parallelogram made. It looks like a vertically oriented parallelogram. Now all you gotta do is make your vector resultant. I'm bringing something long over here. From this origin right here to this intersection point right over here, I have to make my reference horizontal. Maybe I should bring something smaller than this so I don't totally obstruct your view, and this might be just long enough. From right over here to over here, I'm gonna get my resultant line marked. All we have to do for this resultant is measure it in terms of length, and then we'll multiply it by 10 to give our miles per hour, and we'll determine the angulation, and we're done. Let's determine our length over here. Our length over here is going to be 14 centimeters or 140 miles per hour. The plane has dropped from 180 to 140 miles per hour simply because of the opposing wind. All we gotta do now is determine our angle from 0 degrees. We have to determine our angle from 0 degrees, and we can bring our handy protractor and do it. Let's put everything along the reference horizontal and the vertical line and measure this angle, and the angle comes to be slightly past 85, and I would say it's at 86.5 degrees. 86.5 degrees has to be written in the correct designation over here. Do 86.5 and you minus that from 90, you get 3.5. So my direction is north 3.5 degrees east. Let's do our resultant was 140 miles per hour, and the angle of the resulting plane direction was north 3.5 degrees east. Tilt it slightly away from the 90 degree line. Originally it was 75, but the direction of the wind has pushed it more closer to the northerly direction. Now that this old way of analysis is completed, it only makes sense to verify that the technique was good. And the best way to verify the technique is good is now to do this in the classic way of doing this, which is by means of this calculator. We're going to run this question very quickly using a vector analysis and see if we get something close to this. A resultant of 140 miles per hour and in the direction of north 3.5 degrees east, or you can say 86.5 degrees. Let's see if we do get that. You know what we have to do over here. We already have everything we need right over here in terms of our magnitude and our direction. We just have to write these in vector form. The plane was of course 180 miles per hour, and it was cosine of the angle 75, and it was sine of that same angle, the x and the y direction, and the wind of course was 60 miles per hour in a cosine direction of 225 and sine of course of 225. And you know, vector addition leads to the resultant, right? It leads to the resultant. Examples I've shown you. Let's do this swiftly over here. We're going to add this by means of the proper trigonometric function and multiplying it with the magnitude. Let's do the first column right here, my column. I'll do 75 cosine times 180 plus 225 cosine times 60, and I get 4.16 as my x component, my horizontal component. Let's look at the next column. 75 sine times 180 plus 225 sine times 60, and I get 131.4. These are my resultant vector components. But what's my actual resultant magnitude? You know, you gotta do the square of these individual components and square root. Let's do the square of these and square root them. Sum of their squares and the square root. And I'll present you an answer over here. 4.16 square plus 131.4 square, and the square root of that, I'm getting a 131.5. I'm actually getting 131.5. 131.5. Let's see what I'm getting as my angle over here. My angle is arctan of the y divided by the x value. 131.4 divided by 4.16 inverse tan, I get an 88 I'm getting an 88.18 degrees. Now look how far we deviate from our true answer. Well, this right here is our true answer. Look how far we deviate from our custom answer using the old way. I had an angulation of 86.5, but I'm getting an angle of 88.18, so I'm slightly off. But my speed was 140 and my resultant is 131.5. Let's determine our margin of error over here. Let's see how off we are. We'll do our calculated value using the old 140 minus 131.5, and we'll divide it by the true value 131.5 and multiply by 100. I'm off over here in terms of the magnitude by 6.46%. That's what my error is. With regards to the direction, let's calculate our error. It's 86.5 minus 88.18 divided by 88.18, the true value. And of course you can absolute value your negative and you multiply by 100. My margin of error over here with regards to the degrees is 1.9%. So I'm very close in terms of my angulation, but I'm slightly more off. 5% is normally considered acceptable, but I'm outside of the 5%. But I guess perhaps part of the reason is when I was using a shorter ruler, and then I'm redirecting the ruler for the addition of these remaining 4 centimeters, I was making angulation errors over here. I have a 14, and then I had to add another 4 over there, and I must have made an error in terms of these overlaps. But you can see this is exactly how it was done in the old days without the calculator. You would actually have to draw your magnitudes to the correct length. Even if supposedly it was 180, you bring it down to 18, you could have divided everything even further and made it smaller, so long as at the end you multiplied it by that factor. You use your diminutive factor. You can diminish things, but then you have to re-enhance them for your calculation. You can use diminutive factors in these type of calculations. Anyhow, as I'm saying, this is how it was done before the advent of calculators. With regards to the vector magnitude, you have to be very specifically accurate in terms of your drawings, and you have to be very accurate in terms of your protractor usage. But you can see with a margin of error 6.46%, I think I could have done much better if I had a proper size ruler, but my angulation wasn't bad at all. But this is exactly how it was done. The calculator just makes the whole process very easy and smooth. It makes it very much more accurate. But now you have the process laid out to you, how it was done before and how it is done now. Calculators have made things vastly easy. I hope you enjoyed this video. You can always try something out like this on your own. But please like, subscribe and share. Thank you and have a nice day. Bye.